Test, test. Bree, welcome back.
Hi.
How are you doing?
Good.
Good, good. All right, we good? Still got a few minutes. Hey guys, y'all can move this table, move the table around if if you need to tilt it or whatever. You should have your, you want to move that other desk over? A little warm in here, isn't it? A little stuffy in here. Roman, how you doing?
I'm good. Yourself?
Good. Can you hear me okay?
Yes, sir.
Okay. I'm using the mic that I used on that one day. Remember when it was like staticky? I think you had said something
Towards the
about it.
end.
Yeah, towards the end. It was just a loose connection. So you can hear me when I'm, oh, you can't see me. Hold on. There we go. So you can hear me even when I walk away. I don't sound like I'm getting more quiet now. Yeah, okay. All right, 2 minutes. And we'll take the quiz. I'm just kidding. Welcome back. Welcome back. Jair, you doing all right? Yeah. Yeah, we had the margarita machine on Wednesday, but you weren't here. Uh-oh. Okay, got an issue here. Why does it do this? Hold on, got a little issue here. What is it doing? What is it doing? Two, three. Okay, I have a little bit of a problem here. Try this, disconnect it. Try it again. What the hell? Freaking technology, man. My pen is not showing up, and like I touched the thing and it's not showing up in the right place. Try that. There we go. Okay. And there. Okay, well, welcome back, everyone. Hope you had a great weekend. I hope that you have an opportunity to do the homework. Well, I hope you had an opportunity to do the homework. If you didn't, don't fall too far behind because it'll become apparent very quickly that you're behind very quick, right? So, all right, so last class, we were doing 6.2. I said that this section was broken up into 2 parts, trigonometric trig integrals, which we did last time, which is how to handle sine, cosine, secant, tangent when they're mixed up, and the homework gave you kind of an idea of what to expect there. And now we get to the second part, which is the harder part, and that is the trigonometric substitutions. So very important here. It says, after we, what the heck, man? Oh, there we go. After we master the above concepts, that means after we've figured out how to do the trig integrals, then we can now do this, all right? So what we're gonna do is we're gonna make a substitution. Now, we've done substitutions in the past. We did U substitutions, right? So this substitution is gonna be a little bit different. we're going to make a substitution when we see a specific type of integral. And the substitution that we make is going to seem very unnatural, but it's going to make things work out in our favor. Okay, so this new type of substitution that we're going to make is called a trigonometric substitution. So this is not U substitution. U substitution is when we look for something and its derivative, and it's okay to be off by a constant. That was the first kind of method we ever learned. Here, trigonometric substitution, very different. So, oh, I misspelled anti. Oh, well. So here's the general idea. What we're looking for is in the integrand, we're looking for a square root, and then we're either going to be looking for a number squared, a squared, so some number squared, minus a variable squared, or the number squared plus the variable squared, or the variable squared minus a number squared. Let me just write all those out, because in my notes I only have one case. So what we're looking for is in the integrand, somewhere in here, okay, somewhere in there, we want to see one of three possible things. Okay, one of these three. We're either going to see a square root of a squared minus x squared, or the square root of a squared plus x squared, or we're going to see the square root of x squared minus a squared. So just keep in mind here that the first one and the last one look like they're the same, right? But the orders is backwards. And with square roots, you cannot just change the order, and it's not the same thing, right? Normally we can switch the order, but we have to factor a -1 out. You can't do that with the square root because you can't take a -1 out of a square root. So the first and third cases here are distinct from one another. And then the case in the middle can actually be flipped around. You can do a squared plus x squared is the same as x squared plus a squared, all right? So if somewhere in the integral we see one of these three things, we're going to make what's called a trigonometric substitution. And each of these three things requires a different trigonometric substitution. So we have to go through all three today to make sure you understand what to do in each of the three cases, all right? So we're going to start with the first one, a squared minus x squared, all right? So we're not doing an example right now. I'm just trying to get you to understand why the substitution we're about to make works, okay? So here we go. Let's say I start you off and I say you have the square root of a squared minus x squared. And now here comes the substitution. I'm going to let x be equal to a times sine of theta. And you should be going, what the hell? You know, like, why are we replacing the x with a sine theta, right? Like, why? Well, let's just do the algebra and see why. Okay, something really good is going to happen. So, oh wait, am I sharing my screen, Jair? I'm not sharing my screen. Am I?
Oh, you were. Well, like I could see through the board.
Yeah, no. You need the screen. That's the whole point. Okay, now it's better. Yes?
Yeah.
Okay. All right. So let's make the substitution. So everywhere I see an x, I'm going to replace it with a sine theta. Okay, underneath this root. So it becomes square root a squared minus, now I'm replacing x with a sine theta squared, right? Now, when you square that, you square each of the factors. You square the a and the sine theta, right? So this will become square root a squared minus, now the a gets squared and the sine gets squared. So I'm going to put sine squared theta like that. And now they both have a squared, right? So I can factor an a squared out of both of those, still underneath the root. When I factor out a squared, I'll be left with 1 minus sine squared theta. And do you recognize from the Pythagorean identities what 1 minus sine squared theta is? What is it? Cosine squared theta. So that just becomes the square root of a squared cosine squared theta. And now we're taking the square root of both of those, right? Because there's multiplication between them, I can just do the square root of each one. So that should just leave me with A cosine theta. So imagine an integral that has this real ugly algebraic expression in it. We make this weird substitution. This ugly square root is always going to turn into that very nice little expression, A cosine theta. Now, our new integral will be in terms of theta. So at the end, we will have to get back to X. But at least I would rather integrate cosine than that, right? So this looks like it's promising in terms of leading us to being able to find antiderivatives. Does it make sense? Okay, so in the notes, what I do is I kind of summarize this idea. I say, look, if we have a squared minus x squared underneath the square root, then we make the following substitution. X is equal to a sine theta, right? If we do the algebra, it's going to turn out to a cosine theta, right? That's what we just did. So that square root thing turns into this. Now, keep in mind also that if we do this substitution, okay, so if we make this substitution in yellow, then if I differentiate both sides of that, okay, but I take the derivative of both sides, then I'm going to get dx, the derivative on the left, is a cosine theta d theta. This is very similar, like, remember when we made u substitutions, and then we would take the derivative on both sides, and then we'd use that to like go back into the integral and replace the, we'd like play a matching game. Remember, we'd try and match up something in the integral. Same idea here. If we're going to be taking this part of the integral, right, in blue, if we're going to be replacing that with something with theta in it, then the dx in the integral also has to be replaced with something with theta in it. So the dx will always become a cosine theta d theta. Okay. Questions? I mean, it's best to see an example worked out, but are there any questions? Yes.
I still know the validation is for making x equal a sine theta.
What do you mean the validation? Like, are you saying, are we allowed to do it? Or are you saying, why are we doing it? Allowed?
Why is it?
Because you can, why not? If I want to call x a sine theta, I'm allowed to call it that, right? I mean, x is a variable, right? I can replace it with anything I want, as long as when I go back, right? And I switch. So what I've done is I changed the variable from x to theta, right? And then I'm going to do work, and then I'm going to switch it back to x at the end. I just have to make sure that when I switch it back, I follow that equation. That equation in yellow is going to dictate how I switch from theta back to x. I understand your hesitation because you're like, well, wait a minute, we don't know what x is. Why can we just call it this? It's what we're doing. The way I kind of look at it is we're looking at the problem in terms of x, and it's like really kind of difficult to do. So what we do is we say, wait a minute, now I see it through this different perspective of theta. Now I can do the problem. Now I have an answer. Let me switch that back to x now. I don't know if that makes any sense. It's a common thing we do in math. It's just switching the variable over.
Yeah, with your explanation. It's the fancy
Yeah, it's a fancy U sub, except that in U sub, we took something complicated and called it U, right? So you don't seem to have a problem with that, right? I mean, just call that U. What we're doing here is kind of different. We're taking X and we're calling it something complicated, and then we're doing something with it. So it's unique that it only works with the square root of a squared minus x squared. If we don't have that, we don't want to do this substitution because it's not going to work this way. Okay, so in the notes, again, the summary here is that the square root of this stuff will turn into a cosine theta, that dx d theta will turn into this, or if you want, this is the way I wrote it just now, we have this. So this box summarizes everything. If we have square root of a squared minus x squared, we will make this substitution. The square root ugly stuff in the integral will turn into just very simple a cosine theta, and the dx will turn into a cosine theta d theta every single time we do it. All right. So let's do an example. You know, there's a similar, what was your name, sir? Austin. Okay. So in math, everything we do in calculus, at this point, Cal 1, Cal 2, and Cal 3, we're dealing with real numbers, okay? Real numbers. And if you study more, maybe some engineering, maybe it depends, probably electrical engineering, the real numbers live in a larger system of numbers called the complex numbers. And that's where your imaginary numbers are. It turns out that there's some very, very difficult problems to do if all you do is live in the real world, real number system. So if you just look through the, I hate when people say look through the lens. It's like, seems like real trendy. Have y'all heard a lot of people saying it through the lens of, okay, I don't mean it that way. Just if you look at just through the goggles of real numbers, some problems can be really hard, okay? But if you take a step back and realize that you're actually living in a bigger number system, you can do that same problem very easily with the complex numbers. This isn't exactly the same thing, but it happens a lot in math where if you step outside of your little fishbowl into the bigger universe that you live in, sometimes the problems can become much easier. Okay, so here we go. We've got this problem, and this is, I think, where we really start to feel the like, what do you do? That feeling of, okay, how do I do this integral? Because we have, the stuff we learned from Cal 1 that we should be able to go backwards. We've got the power rule. We've got U substitution, basic U substitution. We've got integration by parts, right? We've got trig integrals, but this isn't a trig integral. There's no cosine sines in here, tangents, secants. So I think right now we could say this is probably either a basic U substitution, an integration by parts, or a trig substitution, which is today, right? Let's make sure it's not a basic U substitution. So if this x cubed were an x, I would be going basic U substitution, because 16 minus x squared, the derivative of that would be 2x, negative 2x. And so I'd be off by a constant. The fact that it's an x cubed makes me say no. And I definitely don't want to make the x cubed my u, because the derivative of that, 3x squared, it's here, but it's trapped under a root. So we don't want the derivative ever trapped. So do y'all see why I'm kind of like, okay, I don't think it's U substitution. I don't think it is. Integration by parts, I don't know. Is there anything in this that's making you think no integration by parts? Y'all know what I'm saying? Like if you had to make a table here and do your U and dV, like what would you choose for U? You want to do all that? Put it here? Yeah, and then when you take the derivative of that, right? It gets ugly, but you would have to put the x cubed here, right? You could integrate that. That'd be 1/4 x to the 4th. So that wouldn't be that bad. But the voodoo, right? This part would be a pretty ugly integral. What if you did it the other way around? What if you did the x cubed here and the square root here? The integration's not going to be doable, okay? That antiderivative of 16 minus x squared, right? This going up, you can't do, all right? So thinking no on that, but I do see a square root. I do see a number squared minus my variable squared. So now I'm thinking trig sub, all right? Y'all just stop me if you have any questions. Okay, so trig sub, I'm going to write down what I'm doing here. Trig sub. All right, so I need to identify what's A. What's A in this problem? So 16 is A squared, isn't it? A squared is 16. So the A would be the 4. Got it? That's important because later on, that number does not have to be a perfect square. That 16 does not have to be a perfect square. But we need to understand that A is the square root of that number. So A is 4. And I'm seeing the form, I'm seeing this form A squared minus x squared, right? That's the form I'm seeing. And because I see that form, the trig sub I'm going to make is x equals what? A sine theta. So A sine theta, which for us is 4 sine theta, isn't it? 4 sine theta. Okay, so I think I'm ready to go with this. All right, that was just kind of thinking out loud, like on paper here. So here it comes. I'm going to make my actual trig sub now. Do a different color. X is equal to 4 sine theta. Now, while we're here, let's just take the derivative of that because we're going to need it. So dx will be 4 cosine theta. Don't forget the d theta because you took the derivative. Now, without doing any algebra, without doing this, what will the what will the 16 minus x squared become? What will it become? Anyone? Think back to the previous note. Whenever you have a squared minus x squared under a root, when we do the substitution and do all this algebra, we're guaranteed it's going to wind up at the end to be what? A cosine theta, right? Guaranteed. Now, if you want to show all this work, you can right now. You can do it. But I know the answer is going to be A cosine theta. So I can just from here, just write down that this is equal to 4, right? Cosine theta. Again, to do it algebraically, just take that x, replace it with 4 sine theta, square it, it'll become 16 sine squared theta, factor out the 16, then you'll have 16 times 1 minus sine squared. 1 minus sine squared becomes cosine squared, take the square root of each one, you get 4 cosine theta. I said that fast, but that's what would happen, okay? All right, so now we are ready to rewrite this integral, okay? So I think what I'd like to do, I hope you don't mind, I'm going to just erase this on the side because I want to try and do this all together here. I'm going to grab this, move it over here. Okay, so here we go. Now I'm going to rewrite the integral. This integral becomes, okay, x cubed, right? X cubed. Well, what's x for us now? This is x, right? So if I cube this, I got to cube the 4 and the sine, don't I? So this is going to be, I'm going to write it as 4 cubed, even though we can all do 4 cubed in our minds. Well, maybe, maybe not. Sine cubed theta. Does everyone understand that that's x cubed? Okay. Now, the square root of 16 minus x squared, what does that turn into? 4 cosine theta, right? So we know that that next piece is 4 cosine theta. And then what does the dx turn into? What is dx? It's all this, right? So 4 cosine theta d theta. So we'll play a little matching game. The x cubed here became this, right? The 16 root of all that became this. And then the dx became that. Understand? Now, what are you looking at? That's a trig integral, right? That's last class, right? We got sines and cosines in here. So let's do something. Let's get all those 4s out of here. Those 4s are all constant. How many 4s do I have? 4 cubed and 4 and 4. I have 4 to the 5th, right? I'll figure that out later. I have sine cubed theta, and then I have cosine squared theta d theta. Boom, we're in business, right? We are in business. We have a trig integral now, and now we need to go back to what we learned last class, right? So because it's been a whole weekend, I'm going to go back to last class. And let me go a little faster here. Trig integrals involving sine and cosine. All right. If you have cosine to the n with n being odd, do we have that? No, we had cosine squared. We had squared, right? So we're not going to do that. Okay. If we have sine to the n with sine being odd, do we have that? We have that. Okay, good. So when we see that, what we do is we factor out a single factor of sine, and we use the sine squared equals 1 minus cosine squared to rewrite things. So I'm going to be peeling one factor of sine off to the side right now. So I wasn't lying when I said you have to be able to do the other stuff to be able to do this, right? I mean, you literally have to, because the problem reduces to what we did last time. Okay, here we go. So now I'm going to take this to the next page. Y'all doing all right at home? Yeah.
Yep, doing good.
Okay. So here I go. I'm going to peel off a sine. All right. So when I peel a sine off, I'm now left with sine squared theta. I have cosine squared theta. Here's the sine that I peeled off. So now what I do by peeling this sine off, I know that I have a sine squared that's even. It'll guaranteed be even because it started as odd. So I peel off. Now I use the Pythagorean identity on that. I rewrite the I rewrite the sine squared as 1 minus cosine squared theta, then cosine squared theta, and then sine theta d theta. And now what? U sub. What's the U substitution?
Cos.
The
Or
cos,
cosine.
right? The cosine theta. So U is now going to be cosine theta. Okay. So everywhere I see a cosine, I replace it with U. Now, what's the derivative of this? The derivative of that would be negative sine theta. Do you have negative sine theta? I'm off by a constant. I have sine theta, right? That's no big deal. I'll just make the right side plus and make the left side minus here on this little equation. So I will replace sine theta d theta with negative du. I will replace all my cosines with u's, and the remaining integrals should be doable. So 4 to the 5th integral parenthesis 1 minus u squared times u squared times negative du. I'll pull that negative out, negative 4 to the 5th integral. What do you say we distribute that u through? U squared minus u to the 4th du. So I pulled the negative in front of the du out of the integral completely, and then I just distributed the u squared through, and now power rule, right? Negative 4/5. Okay, here comes my antiderivative. 1/3 u cubed minus 1/5 u to the 5th, all that plus some constant. There we go. Okay, now we have a little bit of a problem. The original problem was x, right? Had x in it, and where are we? Our answer has u, right? So we've got to get from u back to x now. So what is u? Well, let's replace u with what u was. U was cosine, right? So cosine theta. So negative 4/5, this becomes 1/3 cosine cube theta minus 1/5 cosine to the 5th theta plus c. Y'all doing all right? We're only 25 minutes into class here on the first problem. Okay, so we're got from u back to theta. Now we get theta back to x, right? Theta back to x. Here's how we do it. You go back to the original substitution you made, which was this right here, okay? X is 4 sine theta. We're going to go back to that, all right? And I'm going to write that down over here on the side. X is equal to 4 sine theta. From this equation, I am going to create a reference triangle. We did this at the very beginning of class. I told you it would come up again. It's here. So I'm going to divide both sides by 4. And then from that equation, I'm going to draw a right triangle that satisfies the equation. So I'm just going to draw like a generic arbitrary right triangle. I'm going to call this angle theta. And according to this relationship, sine theta has to be x over 4. Sine is opposite over hypotenuse, right? Opposite over hypotenuse. So that means if I label the opposite side x and the hypotenuse 4, then this triangle represents that equation. It's a visual representation of that equation. But what's great about that triangle is that, see, my answer has cosine theta in it, doesn't it? So I can get cosine theta off of this triangle if I just knew the adjacent side. but I do because I have two of the three sides on a right triangle. So I hope you're all comfortable solving for this side. Yes? What would it be? If you solve for that side?
X squared, no, a squared plus x squared equals 4 squared.
Okay, so then when you solve for that, what?
Square root of x minus a.
It'll be the other way around. There'll be a squared 16 minus x squared. That's what this side would be. You can do it for yourself. Just call this side anything you want, and then just, do that squared plus x squared equals 4 squared, and then solve for this side. You should get this. Hey, does that look familiar? That is that weird part of the, right? That was the whole thing that we were looking for in the integral. I wonder if that's a coincidence. I don't know. We'll see. Okay, you ready? So what is cosine theta according to this triangle? Adjacent over hypotenuse, right? It's this side over this side. So everywhere I see a cosine theta, I'm going to replace it with this square root over 4. Here we go. I forgot to tell you how much fun this was going to be. I should have told you all that in the beginning. Okay, so here we go. We have cosine cubed. So I'm going to write square root of 16 minus x squared over 4. Then all that cubed minus 1/5. And then the same thing, square root of 16 minus x squared over 4, but this time to the 5th power, all that plus c. I'm going to clean it up a little bit. Okay, I'm going to clean it up a little bit because I had intentionally kept this 4 to the 5th out here because I kind of knew where we were about to go with this. So let me just clean up a little bit. Any questions on that part? Negative 4/5. Okay, we have 1/3. Okay, watch what I do here. The top 16 minus x squared. I'm going to raise that to the 3/2. In other words, I'm cubing the square root, right? That's what's happening here. I'm cubing the square root. So that's the same as raising it to the 3/2. Now I have to cube the 4 on the bottom, don't I? So I'm just going to write 4 cubed. You understand that? I'm cubing the top and bottom of that fraction. Cube the top, cube the bottom. I'm going to do it on the same thing for the other one. Negative 1/5. Okay, times. This will be 16 minus x squared to what power? 5/2, right? 5/2 over 4 to the 5th plus c. Now, I'm going to distribute this negative 4 to the 5th through here and here. Do you see how when I do that, this 4 to the 5th and this 4 cubed, they're going to kind of reduce out a little bit? I'm going to be left with the 4 squared on top. Do y'all see that on this first one? And 4 squared is 16. So this next line, this is going to be my final answer, I think, is going to be negative 16 thirds 16 minus x squared to the 3/2. That's the first distribution through. What about on the next distribution? 4 to the 5ths going to cancel completely, aren't they? And it'll be plus, yeah, plus, thank you. So it'll be plus what?
1/5.
1/5, okay. And then in parentheses, the whole thing, right? 16 minus x squared to the 5/2 plus c. There it is. Yeah. Well, isn't that something, huh? What do y'all think? Trig sub. So just for fun, should we take derivative and check it? Come on, we can do it. It won't be that bad. Let me do. I'll have to put my glasses on for this. Okay, so here we go. You take derivative of the first part, so I'm do chain rule. So the 3/2 is going to come out in front. What happens when I do that? What am I left with? When I multiply 3/2 times -16/3. -8, right? -8. And then we'll have 16 minus x squared. Now we subtract 1 from that, so raised to the 1/2, times the derivative of what's inside, which is -2x. Okay, that's the derivative of the first one, right? Okay, plus, let's see. Now, when we bring the 5/2 out, it hits this, the 5's cancel, we should just get 1/2. Then it'll be 16 minus x squared. We reduce this by 1, so 3/2, and then times the derivative of the inside, which is -2x. That's it, right? That is somehow the original expression. So let me clean this up. This is 16. I'm doing the -8 and -2x, so 16x. Then that's the square root of 16 minus x squared, isn't it? And then this one over here, I can put those two together. So that becomes minus x. And then this is really, this right here is the square root of 16 minus x squared times 16 minus x squared. So I'm doing this just because I know where I'm headed with this. This to the 3/2 is the same as the square root of it times itself, because this is a 1, that's a 1/2. You add them together, you get 3/2. Now, factor out, what do they both have in common? They both have, let me just factor this out, okay? Let me factor that out of both, okay? Let's just factor that. I'm out of room. Okay, so if I just factor the square root out, what am I left with here? So I've got a 16x from the first one, right? Minus an x, and then still here 16 minus x squared, right? But that's 16 minus 16x, right? Plus x cubed times this. Yeah? Oh, I forgot the x here on this one. Do y'all see those are gone? What are you left with? Square root of 16 minus x squared times x cubed, and that's the original integrand. Yeah, so it worked. All right, so welcome to trig sub. Let's take a look at the next type of trig sub that we can do. Okay, that's how you deal with square root of a squared minus x squared, right? Let's see what the next one is. So did that one. Okay, so here's the next one. If we see the square root of a squared minus x squared, that's what we just did. Here's the next one. Let's do the plus. I'll put this table back up, but let me motivate where it comes from, okay? So we have square root of a squared plus x squared. So the question becomes, what do we do? What is the substitution that we do for this, right? If it was a minus between those, we do a sine theta. X is a sine theta. Here, we do x equals a tan theta. Tan theta. Tangent. Now, let's see why, okay? I'm just going to show this one time, but let's see why this works. If we replace the x with a tan theta, it becomes a squared tangent squared theta. Y'all agree? If I replace that x with this, I get that. Can factor out an a, just like we did before. Sorry, factor out an a squared. We're left with 1 plus tangent squared theta. And what is that from pre-cal? What is 1 plus tangent squared theta? Secant squared theta. So this becomes square root of a squared secant squared theta. And that becomes a secant theta. Hold on, I gotta check something here. There it is. System seems a little slow. Everything's okay. Okay. All right, so what's going to happen anytime we see square root of a squared plus x squared? Anytime we see that, we're going to replace the x with a tan theta, and then this square root thing will turn into, every time, will turn into a secant theta, right? What we have not established yet is what does dx turn into, right? Dx needs to turn into something too. So take the derivative of this. The derivative of that would be a, what's the derivative tangent? Secant squared theta d theta. Okay. So this is summarized in the notes. If we see this in our integrand, square root of a squared plus x squared, then we will let x be a tan theta. This big old complicated thing will become a secant theta, and the dx will become a secant squared theta d theta. So do y'all see how this is similar to this one in the sense that we'll have three things that we need to keep track of: what x is, what the square root crap looks like at the end, and what the dx turns into. Now, should we, yeah, I'll do an example. I was going to go right to this, but let's just go to an example. So let's do this one. All right, so again, you have to kind of run through this Rolodex in your mind going, okay, is this a basic U sub? Is it integration by parts? Oh, wait, I see a square root. You do not want to get into the habit of saying, as soon as I see a square root like that, I'm going to go trig sub. Do not do that, because it might just be a basic U sub. But in this case, it's not, okay? It's not. So I'm going to imagine that you've spent a little time thinking about that and that you've chosen now to go down the road of trig sub. So the trig sub we make here is what is it? X is what? A tan theta. So what is A for us here? So the 9
The
is
3.
always the number squared, right? So
Oh.
A for us is 3. So we're going to make this substitution. X is equal to 3 tangent theta. All right. That's our trig sub. That is our trig sub. Okay, that's our trig sub. Now, what does what's the derivative of this? We'll do that right here. 3 secant squared theta d theta, right? Don't forget the d theta, please. That's the derivative. And also, we know that the square root of x squared plus 9, that complicated thing, really is just going to simplify to be what? We're not going to go through all the algebra. What do we know that turns into?
Oh, I'm sorry.
That's all right. That's all right. 3 secant theta, right? So a secant theta, so 3 secant theta. Yeah? Okay. Are we all good with that? These are the things that are most important right here. What x becomes, what dx becomes, and what that square root thing becomes. And now we just go rewrite the problem, okay? In terms of theta. So we will have 1 over. Okay, x squared, right? X squared is 3 tangent theta squared, right? Which I guess we'll just do 3 squared. We'll do 9. Okay, I guess that'll work. We'll do 9 tangent squared theta. That's the bottom left corner. Next to that, we have the square root of the junk right there, right? All that square root stuff turns into just 3 secant theta. right? And then don't forget, what do we still have? This is the part that students forget. The dx, right? The dx also gets replaced, right? So that dx right there gets replaced with 3 secant squared theta d theta. Now we get some things to go away here. We get one of the 3's cancels, right? And then one of the secants goes away, doesn't it? So what we're left with at the end of this is 1/9. So I'm going to take that 9 that was on the bottom, bring it out. I have a secant theta on top. On the bottom, I have a tangent squared theta d theta. Now, if you go back again to last class, we'll say, okay, well, this right here is a trig integral. It's got secants and tangents in it. The issue we have, though, is that the tangent squared is in the bottom. So if you mess with this for a while, you'll realize that, you know what, the best course of action here is to get everything in terms of sine and cosine. So I'm going to do that right now. I'm going to rewrite the top as 1 over cosine theta. I'm going to rewrite the bottom as tangent is sine squared theta over cosine squared theta. And then I'm just going to divide a fraction by another fraction. So I'm just going to flip it and multiply. So this becomes 1 over cosine theta times cosine squared theta over sine squared theta. I probably don't need to show that step, but I guess it doesn't hurt. One of the cosines cancels. And here's where we are. Anybody have questions on that algebra? Secant squared is 1 over cosine. Tangent squared is sine squared over cosine squared. Flip the fraction up, multiply, cross, cancel out a cosine, and there's where we are. Anyone see how to do that one? U sub, what's the U? U is sine. Why? Because the derivative of it is cosine, and it's sitting right up top, nice and pretty for us, isn't it? So that's a basic U sub. Make U the bottom, just the sine. The derivative of it is up top, and we're in business. So this integral now becomes 1/9 integral. Okay. What is it? What is left here? I'm a little confused. 1 over u squared du, right? 1 over u squared du, because cosine theta d theta is all that up there. And then the u here, the sine theta is the bottom without the squared. So just becomes 1 over u squared du. That is not natural log, right? That is not natural log. You have to bring that up as a u to the -2 and then use your power rule. I forgot the 1/9. 1/9 integral u to the -2 du. So the antiderivative of that should be -1/9 u to the -1 plus c. Which, if you like, you could rewrite that as -1 over 9u plus c. I just decided to bring that u to the -1 down. All right, what's u? Sine theta. So this is really just -1 over 9 sine theta plus c. So we've switched from u back to theta now. And now we need to get theta back to x. So where do we go to get theta back to x? All the way back to our original trig sub. X is 3 tan theta. I'm going to use that information right there. I'm going to draw a triangle off of it. Now, sometimes in problems, sometimes it's like you can get the answer you're looking for by just looking here, like sometimes. But I like to just force students down the road of doing the reference triangle every time. because it's good practice. 3 tan theta, x is 3 tan theta. I divide both sides by 3. And I draw a triangle. Theta, tangent by definition is opposite over adjacent, right? So x over 3. And then we have 2 sides of a right triangle. I'm just going to go ahead and get the third side. I may or may not need it. I don't care. I'm just going to go get it. Turns out to be square root of x squared plus 9 if you do the algebra here. And again, doesn't that look familiar? Square root of x squared plus 9. Wasn't that the original thing that we did our trig sub on? Wonder if that's a coincidence. I don't know. Second time it's happened. It'll show up every time. Okay, it'll show up every time. That's where the whole idea of the trig sub comes from, is this triangle. Okay, so sine theta. What is sine theta? Sine theta is, well, you know what? I'm going to do something. Would you all agree with this? Isn't this negative 1/9 cosecant theta plus c? I mean, I could write it that way, couldn't I? Like 1 over sine is same as cosecant. So I could write it this way, and then just cosecant is a reciprocal of sine. Sine is adjacent over hypotenuse. So cosecant should be hypotenuse over adjacent. I'm sorry, it's totally messed that up. Hypotenuse over opposite, right? Yes, so I'm just going to write the negative 1/9. Then I'm going to write the square root of x squared plus 9 over x plus c. That should be it. Are we having fun yet? No? Don't lie to me. I know this is fun. I realize this is a lot. I mean, you have to kind of keep track of. There's lots of places to make little mistakes, right? The important thing is, are you approaching the problem correctly? Are you making the correct trig sub? Are you doing everything? Are you replacing everything correctly? Because if you just miss one little thing, right? One little thing. If you accidentally put secant instead of secant squared, it's over, right? So lots of little places you have to be meticulous. I won't check this one. I could. If I checked it, I would have to do a quotient rule derivative, right? Okay, so that's 2 of the 3. Any questions? We're halfway through class. Good. Okay, the last one is if you see the square root of x squared minus a squared. Notice the position of the variable and the constant, right? If it's a squared minus x squared, we do the a sine theta. But if it's x squared minus a squared, we do x is a secant theta, a secant theta. The square root crap turns into a tangent theta. And the dx is just the derivative of this, which is a secant theta tangent theta d theta. Do you all want me to show you how this square root turns into this, or do you get the idea now? I don't care. You got it? It would be the same setup as the other 2. We're just going to take this, yeah, this is what would happen, okay? And we're just going to do an example. I'll copy this. Your formula sheets. I know last class we were talking about the trig sub formulas. On the formula sheets, it shows you, oh man, does anyone have it, the trig sub formula sheet? I think it's not in my, yeah, let me just look over your shoulder real quick. Look at the bottom box there, Cruz. It shows you, right, the 3 different expressions on the left-hand side, and then it tells you what substitution to make, right?
Yeah.
What does it not tell you? It doesn't tell you what the dx is, and it doesn't tell you what that square root thing turns into, right? So on your formula sheets that you can have for the class, it'll tell you if you see this, use this. What it doesn't tell you is what that turns into and what the derivative part is. That's not on your formula sheet. Be aware of that. That means you're going to have to learn these. Okay, you're going to have to understand what this square root turns into. All right, and I think with the practice and time, you'll start to pick it up. Any questions? We're gonna do another one. Wait, I was gonna go drop this off over here. That's what we're gonna use for this next one, I think. Let me go to the problem. That's kind of boring. We'll do it anyway. Not boring, but it's. So this is a problem where they want us to find the antiderivative of this, but they don't tell us what A is, which means our answer is just going to have A's floating around the whole time. All right. So the trig sub I'm going to make is exactly what's above here, right? I'm going to do x is equal to A secant theta. The derivative of that will be A secant theta tangent theta d theta, because that is the derivative of secant, right? Of A secant theta. And then the square root of all that crap, x squared minus A squared equals A tan theta. Okay. Rewrite the integral. 1 over what? A tan theta. D theta, and we're ready or no? No, that's a huge mistake, right? Because I just replaced dx with d theta. That's not what dx is, right? Dx is all this stuff, right? So it's A secant theta tangent theta d theta. And actually, we get some pretty good stuff happening, don't we? We get the A's to cancel. We get the tangent thetas to cancel. And all we're left with is integral secant. Oh, I don't like that color. All we're left with is integral secant theta d theta. Right? And what is the antiderivative of secant theta? Careful. Yeah, secant. So we did this last class. Last class, we did this one. This was the one, oh, that's the bonus problem that was due today before class. You were supposed to email it to me or bring it in. Bring it in, right? Here? Yeah. Okay. This was the one we did in class where the secant theta, where I said someone had like suffered and finally figured out what to do here, right? And I said you would never be expected to figure that out. So if you were to run into this integral on a test somewhere or somewhere in your homework, you go to your formula sheets, okay? And this was natural log of secant x plus tangent x. Oh, so that's where we are. Wrong day. So this will be equal to natural log of secant theta plus tangent theta plus c. So that's a formula on your formula sheets. And now I need to know what secant theta and tangent theta are, right? I need to know them both. So I'm going to go back up to our information here. See, and remember how I said I like to force students to draw a triangle, right? Notice on this problem, you can actually solve for secant theta right here, can't you? Secant theta would be what? If I told you to solve for secant theta, it would be what? X over A, right? And then notice on this one, you could solve for tangent theta. Wouldn't it be that square root of all that stuff over A? So you could actually get this answer because both secant and tangent are up here. I'm not going to do that. Okay, you could, that's fine. You'd be done already. I'm going to draw the triangle because it's just never, there's no such thing as doing this too many times. Okay, so here we go. I divide both sides by A. By definition, secant is which side over which side? Opposite over hypotenuse is cosine. Right? Sine is opposite over hypotenuse. Secant would be the reciprocal of cosine, right? Cosine is adjacent over hypotenuse. So that's opposite, sorry, hypotenuse over adjacent. So that means my hypotenuse should be X and my adjacent should be A. And then the other side you can get by solving, and you'll get X squared minus A squared. Hey, there it is. It appeared. And now I can write my answer. Natural log, absolute value. Okay, secant theta, we just said was hypotenuse over adjacent, plus tangent theta, which will be opposite over adjacent. And yes, you could put both of those together into one fraction because they both have the same denominator. But that's good enough. We're good. All right. Questions? You've now seen the 3 different trigonometric substitution types of things that you can run into. All right. You ready? Time for you to do one. Well, maybe not. Hold on. I'm not sure y'all are ready for this one yet. Let me, do y'all want to do one before we do this one? Do you want me to give you one to mess with? Just to, or do you just want me to do this? I don't. You want to do one? Okay. So let's do this. This will be fun. Let's go pull up an old test. Let me see what I got here. Let me see what I got. Just going to look in here for 2414 exam 2. Oh, there they are. I better not pull them up completely up here. Sure you'd like that. Okay, let me see here. Here's a review. I could do that. I don't mind opening up a review. There you go. First 2 problems on the test for trig sub. Or that's a review. So what do y'all, why don't we do this? Why don't we let like, why don't this group, why don't y'all try one? Okay. Or do you know what? No, hold on. It has the 9 in front of the X squared. We're not ready for that shit. Everybody do 2. There we go. Everyone do 2. Yeah. Can you all see it? I'm going to move it up a little bit so you can see. There we go. All right. Let's see. It's 10 o'clock. Let's go till, let's say 10:10. Let's see how far you get in 10 minutes. You may not finish. Main thing is if you can get the trig integral set up, that would be great. Roman, Jair, and Javier, remind me when I come back to unmute my microphone. Okay, I'm going to mute it real quick. Is anyone completely stuck? Like, can't get the plane off the ground at all? I can come help. What's that? What do you got?
You said to remind you about your microphone.
Oh, yeah, I did it. Thank you, though. What'd you do for X? Let me see. 4 tan theta? Okay, that's right. Okay, so then 4 secant squared. That's 4 secant, so. Is that tangent to the 5th? Nothing goes away, huh?
Just stop looking at something.
Okay, you're on the right track. Yeah. I'm coming. Come around this way. All right, what you got?
From this point, would you leave the tan?
No, you cancel them, but let me just make sure. See, so why'd you, oh, it was plus. You wrote it down wrong.
Oh,
That's,
Damn it.
yeah, I was like, why does that not look like anyone else's? Well, that changes your trig, sub.
yeah.
Yeah, that problem would be really hard to do, actually.
Okay.
Secant to the 6 would be really tough.
I don't know why.
Yeah. Yeah,
Makes every-
that'll make life at least a little better. Y'all getting somewhere? 14th. So hold on. Here to here, did you ever integrate? I don't think you ever found the antiderivative. Yeah, I think that's an issue. Yeah. While you're working it, I'm going to start working it myself. Okay. I'm going to start working it on the board, and then we can kind of see if we're at the same place. Make any progress at home?
Yeah.
Yeah, somewhat.
Okay. All right, here we go. That should be your trig sub. That should be your dx. And that should be what the square root turns into. Okay. That should be everything rewritten. Does anyone know what to do with that? How many of y'all got to that?
Would it be like factor out the 5 to get like a tangent to like an even power?
Factor out a tangent. Is that what you said?
Yeah, or like not factor, but like move one to the side.
Uh-huh. Yeah, just like peel it off to the side.
Yeah.
And they get everything rewritten in terms of secant so that you can make a substitution. That I think that's now I saw someone turn it into sine and cosine. That works also. Okay, if you turn everything to sine and cosine, it'll work also. I'm going to do it this way though. I'm going to go 4 to the 5th integral tangent to the 4th theta, then secant theta, tangent theta, d theta. So this is based off of last class. if we have a tangent to the 5th power, odd power, we can peel a tangent off like this and then rewrite the tangent to the 4th. Well, I'm going to rewrite it as tangent squared squared. Just save myself a line here. And then tangent squared becomes secant squared theta minus 1 squared. And then I still have the secant theta, tangent theta, d theta. Who was it at home who said that? I didn't
Me.
see. Is that what you have, Jair, so far?
Yeah, yes.
Okay, good. So by doing it this way, you can make a u substitution of u is secant theta. And then du is secant theta, tangent theta, d theta. So now we're just at a basic u sub. And it turns into integral 4 to the 5th, integral u squared minus 1, all of that quantity squared. And then what we did last class, we just multiplied that all out. Like expanded it. So it becomes u to the 4th minus 2u squared plus 1 du. Here comes the antiderivative, 1/5 u to the 5th minus 2/3 u to the 3rd plus u plus c equals ... I'm not going to take it any further. Now you got to get u's back to thetas, thetas back to x's. Okay, what do y'all think? Okay. I'll leave that up for another 30 seconds, and then we're going to move on to another problem. Any questions, though? Okay. So I had put another one up here, this one here. So I have to walk you through this first time. First thing, no basic u sub, no integration by parts, but I also don't see a square root. Like technically, I have to kind of squint my eyes a little bit to see it. It's x cubed over the square root of 4x squared plus 9, but all of that cubed dx. See what I'm saying? Now I see that I have the square root of, oh, wait a minute, I don't have the square root of x squared plus a squared, do I? Because I actually have a number in front of that x squared. That's the first time this has happened. And it's not good because the formula only works if it's x squared plus a squared, or a squared minus x squared, or x squared minus a squared. We can't have a number in front of the x other than 1. Well, that's not a problem. I'm just going to factor the 4 out. Okay, so a little bit of algebra here on the side. If we have the square root of 4x squared plus 9, I can rewrite that as the square root of 4 times x squared plus 9/4. Right? We can always factor out. We can always factor out a number in front, right? As long as we change that second number to 9 divided by that number. That seemed like a fair move. And then I can take the square root of each of those. So I take square root of 4, I get 2, and then the square root of the other part becomes this. Do y'all agree with the algebra on this? So my integral becomes integral x cubed on top over, okay, in parentheses, something's being cubed, dx. The thing that's being cubed is the 2 and the square root of x squared plus 9/4. I'm going to go one more line before I start doing anything. I'm going to pull out a 1/8 integral x cubed over the square root of x squared plus 9/4, all of that quantity cubed dx. Y'all see how I got the 1/8 on the outside? I went ahead and cubed the 2 and then cubed the root. When I cubed the 2, it became an 8, and then it was free from the parentheses, so it came out as a 1/8. This root is still being cubed, so I just have to write it like that. Any questions? Okay, I'm going to do a trig sub, right? I see a plus sign between these two. And that's the one that's a tan theta, right? What's a? Be careful. What is a here? 3/2, 3/2. A is the square root of that number 9/4, right? If that was a 9, it would be 3. If that was a 16, it would be 4. If that was a 5, what if that was a 5? What if that was 5 right there? What would a be? Square root of 5. That's what it would be, okay? So a is always just the square root of that number. So for us, x will be equal to a 3/2 tan theta. Dx will be equal to 3/2 secant squared theta d theta. And the square root of all that crap we know is going to turn into 3/2 secant theta. We know that because we've studied trig subs now, and that's what happens when you have this form. Any questions? Ready to replace everything? Here we go. 1/8 integral. Okay, the top is x cubed. So I've got to cube the 3/2. I'm going to take the 3/2. I'm going to cube it. I've got to cube the tangent. So tangent cubed theta. That's the top. That's x cubed. Over, now be careful here. The square root of all this crap here is this, right? 3/2 secant theta. But we have to cube it, don't we? So I'm going to do the 3/2. I'm going to cube that, and then I'm going to take the secant theta, and I'm going to cube that. So that takes care of the bottom. I'm still missing what? Dx. Dx was 3/2 secant squared theta d theta. Lots of canceling here. The 3/2 cubed and the 3/2 cubed go away. The secant squared goes away, and I just have one secant left on the bottom. I still have the 3/2 too. So I'm going to pull that out as a 3/16. Right, 3/16. The 3/2 comes out, hits the 1/8. I'll have a tangent cubed up top. And on the bottom, I still have a secant. Now, on this one, I think I'm going to go to sine and cosine. The reason I'm not going to peel a tangent off here, anything like that, is because of the secant in the denominator. So I'm going to just go to sine and cosine. This becomes 3/16 integral. Let's see, the top tangent cubed is sine cubed theta over cosine cubed theta. And then I'm dividing that by what? 1 over cosine, right? Which is the same as multiplying it by cosine over 1. So I'm not showing that step, you know, I'm trusting that you can just rewrite this and flip the bottom fraction up like that. And then cancel one of the cosines. You know, still good? Oh, that's a squared. Sorry, that becomes a square now. So we are at 3/16 integral sine cubed theta over cosine squared theta d theta. Anybody see it? Anyone see what we can do here? Oh, take a tangent out, like do sine squared over cosine squared, and that would be a tangent squared, and then that would leave us with a sine, wouldn't it? So if we did that, you're saying, look at that as tangent squared theta times sine theta, sine theta d theta, like that. The only issue I have with that is I don't see like a u du, like an easy substitution.
Could it be 1 over cosine times sine cubed?
You could do, what about, we have two cosines though. Did you see me in 1 over cosine squared?
Yes, I'm sorry, yes.
Yeah, you could do 1 over cosine squared times sine cubed, but you cannot do those individually though, right? Because we still have multiplication between them. So you can't look at those as two different problems. Some identities maybe. How about this? Peel a sign off to the side. Just one of the signs. If I peel a sign off the top, then do you agree that this sine theta d theta is the derivative of what? That's the derivative of what? Cosine, I mean, we're off by a constant, but cosine. So if I just rewrite all this in terms of cosine, we'll be okay, right? So I can rewrite this. Oh, I don't know why I put 13 in front. Sorry about that. 3/16 integral. Why didn't I rewrite the sine squared as 1 minus cosine squared on top? This is all legit, isn't it? I mean, I haven't done anything wrong. Like I haven't broken any algebra, haven't I? Now I make a u sub. U is cosine theta. The derivative of that is negative sine theta d theta. I don't want the negative, so I'll just change that to a plus and make my du negative. And then I'll rewrite the whole thing. I will have a negative 3/16 now because that's from the negative du off the back. And then I will have 1 minus u squared over u squared du, right? That's it. Split that into two fractions, right? 1 over u squared minus u squared over u squared. So this becomes negative 3/16. And then it becomes 1 over u squared. I'm going to write that as u to the negative 2, and then minus 1 du. So I did 1 over u squared. I know I'm going to need to integrate that, so I rewrote it as u to the negative 2, and then u squared over u squared is 1, and I'm there. Integration time. Okay, antiderivative of u to the negative 2 is negative u to the negative 1, and antiderivative of 1, what's the antiderivative of 1? U in this case, right? Because our variable is u. This is negative 3/16 times 1, negative 1 over u minus u plus c. I'm doing it that way because I'm about to replace u with something. What was u? Isn't it cosine? It was cosine, wasn't it? So this one's going to be 1 over cos, right? And it's going to be just cos, right? 1 over cos and then minus cos. So I'm going to write that as negative 3 over 16 minus 1 over cosine is secant, and then minus cosine theta plus c. Jeez. I'm going to distribute that through just so I can get rid of that double negative. Those double negatives make them positives. Now we need to know what those are in terms of x. So we have to go back to our original substitution, which I've forgotten a long time ago. We did a substitution. It was x was 3/2 tan theta, right? 3/2 tan theta. Okay, this is going to be a little interesting because I need to set this up as a proportion. So I'm going to multiply both sides by 2 and divide both sides by 3. So I get tangent theta is, see how I multiplied by 2 on both sides to clear the fraction and then divided by 3 to get rid of the 3. And so I get 2x over 3 is tangent. So if I draw a right triangle, if this is theta, tangent is opposite over adjacent, then this side will be the square root of 4x squared plus 9. That look familiar? Square root of 4x squared plus 9 is back from the very beginning, right? Secant, reciprocal of cosine, right? That's what that is. So that's the hypotenuse over the adjacent. And then plus 3 over 16. And now cosine, which is the adjacent over the hypotenuse. Plus c. We're done. We can maybe clean up a little more. These 3's cancel. And those 3's multiply to be a 9. But for the most part, we're there. Yeah. Trig sub, man. It's brutal. Lot to do there, right? Okay. Y'all feeling wobbly? A little bit wobbly? Yeah. I've got more. One of my favorite problems right here. This will be our last one of the day. So this problem is good because for the first time, it's a problem that does not look like what we need to do trig sub. You all see that we have a square root, right? So we're happy about that. With square root, and we've done trig subs with square roots. It's not a basic U sub. It's not an integration by parts. We're like, what the hell, right? This doesn't look like square root of a squared minus x squared, or x squared minus a squared, or x squared plus a squared, right? Because we've got that third term in the middle, don't we? That 6x causes a problem. So the first step is to complete the square. All right, we're going to complete the square first. So that's a college algebra topic, right? So this is where in a class like this in Cal 2, I'm going to see how people learned how to complete the square and whether or not you learned it, I'm not going to say correctly, but did you learn it the way that is going to help you here? Or did you learn it the way that's actually going to hurt you? So let's talk about completing the square, and then we'll get back to this problem. If I take 9x squared plus 6x minus 8, and I ask you to complete the square, does anyone remember how to do this? What I'm even asking you to do. The whole goal of completing the square is to make it look like this whole thing is going to turn into something squared plus or minus, I'm not sure what, but something else squared. That's what completing the square does. It takes a trinomial and turns it into something squared plus or minus something else squared. That's what the process does, all right? Now, anyone recall the process at all? Like anything about how to complete the square? That's factoring. So you're trying to factor, right? No. So I'll remind you, okay, this is why we're doing this. I'll remind you. The first step to completing the square is that this number in front of x squared has to be a 1. Okay, this number cannot be a 9 to do this. So I'm going to factor a 9 from everything. Okay, so I'm going to factor a 9 out. That leaves me with x squared plus 6 over 9x minus 8 over 9. Now, I know that that seems weird, but that is a legal move, right? If I pull a 9 from everything, then if I distribute this 9 back through, I will get this original expression, won't I? Okay, that's the first step to completing the square. The second step to completing the square is that you take this number that appears in front of the x, including its sign. Anyone remember what to do with that number? Divide it by 2. You take that number and divide it by 2. All right. So we're going to take this number 6 over 9 and divide by 2. That's old school division, right? That's the old school division symbol. What I really mean is take 6 over 9, divide by 2, which is really the same as taking 6 over 9 and multiplying by 1/2, right? That's dividing a fraction by 2 is really the same as multiplying it by a half. So this becomes, let's reduce this fraction once we finish this. 6 over 18, what's that? 1/3? Okay. So we divide by 2. Why? Because this is the way we do completing the square. This is the process. Anyone remember what to do once you've done that? Square that number. Take that number 1/3 and square it. So all this is kind of side scratch work, and that gives us 1/9. Does that ring a bell? Take that number in front, divide it by 2, square it. Does that at all ring a bell? No, it's okay if it doesn't, but you'll have to go back and relearn it, I guess. So completing the square, trinomial, right? 3 terms. Make sure that the leading coefficient is a 1 by factoring out whatever number you need to. Then identify the number in front of the x term. In this case, it was plus 6/9, and divide it by 2. Once you divide it by 2, you square it. Now, that's the process. Now, what do you do? Anyone remember what you do with that squared? With that number that we squared, the 1/9. What do we do with it? Anyone remember? No? So this is where in college algebra, usually what you do is you take that 1/9 and you add it to both sides of the equation. It doesn't ring a bell? Good. That's good, because that's not going to help us here because we don't have an equation. We do not have an equation here, so we cannot add anything to both sides of an equation. So if you didn't learn it that way, fabulous. You're not going to be confused then. So, but this is still tricky because now here's what you have to do. You have to look at this. Can I reduce that 6 over 9? Just make it 2/3. Is that all right? Okay, I'm just changing that 6 over 9. I should have reduced it earlier, but okay. So does everyone agree that next to that 2/3 x, there is a plus 0, then minus 8/9? I'm not asking you whether or not like why. Just do you agree that next to this there's a plus nothing? Okay. Now what I'm going to do is the way I'm going to write that plus nothing is going to be very clever. Watch. I'm going to go 9x squared plus 2/3 x. Instead of doing plus 0, I'm going to do plus 1/9 minus 1/9. Now, where did that 9th come from? Well, that was that special number in green that we found, right? When you do this process of completing the square, where you take that number in front and take half of it and then square it, and you get this magic number, 1/9. The reason we do it is because if we rewrite this and we rewrite this with a 0 here and put that 1/9 here and here, added and subtracted, that's still 0, right? But by doing it, what can we say about the first 3 terms? The first 3 terms now are what we call a perfect square trinomial, meaning it's guaranteed to factor. Not only is it guaranteed to factor, it's going to factor a very special way. It's going to be x plus 1/3 squared. Those three terms right here is this thing squared. Where did the 1/3 come from? That 1/3 is always this number here. Now, if you don't believe that that's true, just go to the side and do x plus 1/3 times itself. And do your FOIL. And I promise you, when you're done, you will get the first three terms here. Promise. Okay? So we still have in front of this a 9. And then what about these two together? That's -1. Completing the square. Go back. You're going to have to review, I think. All right. So there we go. Yes? Back to the original problem. This problem actually becomes the integral of 1 over this. I don't like that. 1 over the square root of that thing that we just completed the square on. And we said it was what? 9. And then in parentheses, x plus 1/3 squared minus 1 close parentheses dx. Isn't that what we did? Yes. Now, what about this 9? I can pull that out as a 3, can't I? And just take that out of the root completely? Or sorry, out of the integral completely. So I'll pull it out as a 1/3 integral 1 over the square root of x plus 1/3 squared minus 1 dx. Okay, you good? Does that look now like a trig sub problem? Kind of. Let me help you see it. I'm going to make a quick u sub. Just watch my quick u sub. I'm going to let u be equal to the x plus 1/3. Okay? Real quick u sub. Du would be what? 1 dx, right? Du is dx. Let me rewrite the integral. 1/3 integral 1 over square root of, okay, what is the x plus 1/3 squared? U squared, right? Minus 1, and then dx is du. Now, does that look like a trig sub problem? Yes, but instead of x squared minus a squared, it's u squared minus a squared, right? So I would make a trig sub here. What would my trig sub be? U equals, not x equals, right? U equals u, because u is my variable. What's a for us in this problem? 1, right? So a, so 1, and then what's the substitution you make when you have your variable squared minus the a squared? What is it? Variable squared minus a squared, not secant. It's the last one we did, right? We never ran through it, right? Variable squared minus a squared. The variable, in our case, it's u, right? Not x, is a secant theta. So this is going to become a secant theta. Du would be secant theta tangent theta d theta. And the square root of u squared minus 1 equals tangent theta. I'm out of time. Yes.
I noticed that the 1 over the square root of 2 squared minus 1, it looks the same as cosine hyperbolic.
Wait, which one? What are you talking about?
Yeah, in the.
Oh, for the formula for the, like on your formula sheets?
Yeah, it looks like.
Got you. Like, you can just go straight to the answer. Is that what you're saying off the formula sheets?
Is it here? No, I'm just saying that it looks like the derivative of.
It looks like it. Yeah, let me see here. Formulas. It's going to be hard to see. So on your formula sheets for antiderivatives, right here, what did we have? It was the variable squared. Sorry. You can use anything on this sheet right here, which I don't see that.
No, it's page 5 on the inverse hyperbolic.
Got you. Okay. That one right there. I would be okay with you using that. That'd be okay. That'd be okay. Yeah, you could just go straight back to this. Yeah. But it would not hurt you to run through it. It's not too bad from here. The hardest part is getting it to this, like getting it here, completing the square and doing all that. Okay, so where are we? I mean, I'm going to say that we are officially done with this section in terms of there's no new like trig sub is trig sub, okay? But you've got to practice, okay? So please make sure you're trying your homework. I will come back next time on Wednesday, and what we'll do is we'll kind of wrap this section up. There's a few more problems I want to do in here, but do your best on the homework for this. And if you haven't done the first half, you got quite a bit ahead of you. So have a great day, everyone. Yes.
Will you open up the Dropbox for the extra credit for last?
Did I say I would put a Dropbox, or I thought it was people at home email it to me, people here bring it to me, no?
Yeah, the people here bring it, and then for people that are out, you could
Email, yeah.
Can we email it?
Do you have it?
Yeah.
Okay, well, you can turn it in. Yeah. Yeah, if you have it, you can turn it in. I should have grabbed it at the beginning of class, but if you have the bonus, you can bring it up to me. If you don't, then, and those of you at home, make sure you email it to me. Like in the next 10 minutes. Okay, we are ending meeting.